Okay, do I start?
Yeah, you can start.
Okay, so welcome everybody to my talk about the research software engineering workflow that we have developed for OpenFOAM and university groups. And we're going to look at this process, but as in every good simulation, I'd like to set some initial and boundary conditions first. And what are the boundary conditions that we often have in university? There's a publish or perish culture in which we prioritize the publications and the papers of scientific software, where the software is not the actual product of our process, but the publication is what gives us credit and what is our goal. Accordingly, dedicated resources are lacking, especially in terms of funding, but also in terms of knowledge, time, and effort. There are some programs, but I feel like, especially in Germany, where we are from, my group is from, there's less dedicated resources for this matter. This is subject to change, though, but very, very slowly and starting from a basically non-existent level. The third boundary condition we have is that most of the coding persons are PhD students who will rotate every 3 to 5 years, postdocs maybe even more often. And that means that one person is working on the code, leaving, and another is supposed to pick up what that person has left. But oftentimes there is not even an overlap between those persons. So it's not, there's no interaction between those two persons who would work on the same code, and there may be other collaborators, but they're not really that much into the code, more coming maybe from the mathematical modeling side, or actually in the experimentalist. And the third obstacle we have for developing high quality code is that research software engineering, software design, software development processes, and partially not even data management are mandatory part of the CSE curriculum. For we usually have people coming from mathematics, engineering, or physics, and as far as I know, not even in informatics, it's always part of the curriculum, or at least not mandatory to have knowledge of processes involved herein. So what did this lead to? Many imagine Betty being a research software engineer, or just a person wanting to use or further develop OpenFOAM. You find code that is not tested or only partially tested. It's not automated, the testing. So you're having problems getting to run the tests because OpenFOAM versions changed, because you're running maybe on Windows instead of Ubuntu, or having different compilers. And obviously, we won't expect software that has documentation, or at least no documentation that is up to date. So it's really a mess. And then also adding up, there might be different versions. We know of papers that that describe one solver for a specific problem, but actually looking under the hood, we found it had 3 different solvers, all implementing the same model, but for some reason it actually were 3 different solvers. And in that part, we were actually lucky to find code at all, because oftentimes you don't find the code, or at least not the specific version that was used to generate anything that was published already. So what can we do better? For research to be reproducible, and that is one of the common pillars of science, we should publish the source code and the research data. This also benefits ourselves, as it should increase our publications impact, our visibility, and the easiness for people to collaborate for us, which will open new ways for new research ideas, and overall increases the value of our scientific work. Quick word on that: if you imagine, including all the costs, a PhD student costing 100,000 euros per year, putting out 5 papers, so consider one paper the worth of 100,000 euros. And if there is no code or no data linked to that publication, then all that is left after your 5 years of work and 500,000 euros from taxpayers' money are 5 PDF documents, 40 pages each. So what is the first step to go against that? Take only a couple of hours, honestly, to document and archive your data. Cite them in your article. This will already help a lot. If you consider how often do you write an article, say half a year, if you spend a whole day just to archive it and to cite it, what probably is conservative estimate, then you're having 2 days per year for being able to reproduce your own research. Furthermore, papers are judged in the peer review process at looking at your diagrams, at your tables, and well, if you don't provide anything more than those nice painted pictures, peer reviewers are, to be honest, hardly able to judge your results. And yeah, all what is done with those diagrams is that actual conclusions are considered from that. So a diagram might lead to actions in the real world, or to new insights where a model can be applied or not be applied, or if it should be investigated further. So these results actually do matter. And now, not only is it important that we find those data, but we would like to get a little more insight on them. So please do version control, and on the code, also on the post-processing script, use simple data formats that are readable now, readable in hopefully 10 or 20 years, and without proprietary software, and upload all of that to data archive, or and cite those data in your publication. And if you are able to do it, in case we are not speaking about hundreds of gigabytes, also try to archive your primary data. Primary data being the data OpenFOAM puts out, and not the diagrams. 1 second. Yes. So what does this all lead to? Sorry. You write your journal publication, and you have your code and you have data. So in the journal publication, link to your code that is in some Git repository, and also link to the archives. In these archives, depending on your use case, you might upload the primary data, so really the output from OpenFOAM, the secondary data, meaning the graphs and pictures, and the values of these pictures also. And please also upload the software itself in the current state that was used to publish or to generate those results and to be cited in your publication. Likewise, in the uploaded data to the archives, include the DOIs or the URLs and appropriate data to find application that describes the data into software, and likewise. And for you to see how that might actually look like, let's go to that. It's a bit slow today. Never mind, I cannot open that while presenting. So this link gets you here. And you see we have geodatalib, which is basically an archive like Zenodo and so on. And you have we have a minimal example here is a collection where you have the report, the data, and the code. Now, if we take a look at the research report, this has a DOI, and we have just very little text in this case, but referencing the code in its archive version, referencing the GitLab repository where the code is and would be further developed, and also the research data. So now from the code, you could find the data, the code, also the living repository. And yeah, so have a look at the code. Here are the artifacts, basically what comes out of the CI pipeline. And if you open, sorry, Can have a look at it. It's just a CSV file working on every computer, and we have just the data we need for producing any visualization. Okay. And we have a Jupyter notebook that goes with it and that describes what is actually there. Now, instead of running that, I will go to the kit. You see, we are already there. Again, here in the repository, the report and the data and code are mentioned, so you can find anything that belongs to this repository, and can also have a look at the latest pipeline. And if we go into the visualization stage, download the artifacts, we have the same data that we already have. Okay. So that is that. For the moment being, maybe that would be a good point in time to take questions. I see none in the chat. Looks like there are. All right. So I already mentioned version control. The cross-linking that we just looked into gives us some new colors on this diagram. You just have your main or master branch. You have a research idea, and every idea should be represented by one branch. And so what happens, you do your development as usual, and then at some time you submit to a journal, and you tag that commit, you upload the code to a repository, you link that in the paper, and so like we just looked at, and wait for the review. There might be some further development, either coming from a review, or maybe you have some more cleanup or ideas you implement. And assuming we will have some updates, you will repeat the process once the publication is accepted. And then, of course, merge that into main. So this is just another branching model. And now for the fun part, there's of course CI. I assume many of you know what it is. It basically helps us to reproduce the results from any version of the software, and makes sure that when we rewrite code or add new features, we do not break any existing code or functionality. And just a more sustainable way to grow our software, making sure we test numerics all the time. So what we already tapped into was in the yellow part, so the CI pipeline produces some results and shows them or produces some CSV files, but also some diagrams or tables in Jupyter notebooks describing what was done in that test. And you can download those files and include them in your publication. We will now go a little bit into those parts of this workflow that we haven't touched yet. So without CI, what we would do is looking like this. We have results that are not satisfactory to us. We work on the algorithm, we compile the code, and then for some studies and test cases, we prepare a study, we run it, analyze the results, and in some cases, we move the results to a repo, compare old and new results, and do that over and over again until the results are satisfactory. Now, of course, this takes a lot of time. By starting the studies, you lose time. By analyzing them, you lose time. So you will end up not checking them and also not checking the live, but just whenever you have time for that and are in the office. And at the end, only you know what you did in there, where you copied files or did some shell commands to run and post-process your results. So as soon as you leave, reproducibility will be gone. And also, for convenience, you will skip or forget some studies and tests and lose the overview, what has been done and what hasn't. So considering this, we can divide the sort processing into what we want to do and what we hope we are good at and what we know that the computer is good at. And basically this modifies our workflows. So we work on the algorithms, hit a button, let the computer do all those jobs, and just at the end of the computer running all the tests, we judge the results and see if we are happy or need to go back and work on the algorithm. That's all we do. Now, since we automated all of this, everybody will be able to execute that without any additional knowledge of pre-processing, post-processing, or any settings. And this also helps us in that way that we inherently have some sort of documentation, at least in the sense of how do I run the software and what is the expected outcome, and where it might be applicable. It's not a silver bullet on documentation, but it's helping a lot. And of course, it's guaranteed in some sense to be up to date, because as soon as the tests are not up to date, they will fail. And getting rid of the manual testing that takes a lot of time and is prone to error, we have done the testing in continuous integration, and this will start on every new version of code that is in the repository. It's automatically run, and we'll come to that in a moment. And so all this testing and visualizing has to be orchestrated, and this is done in a YAML file. And that we add to the repository. We'll take a look. Oh, I'm not need to drink. Okay. So again, we add a text file, so-called YAML file, to our repository, and in the text file we describe the CI pipeline, and then GitLab automatically creates a pipeline from this file and basically does most of the rest for us. There's one thing, of course, this pipeline needs to be run on some computers. There are shared runners, free runners on gitlab.com, limited capacity, but they are free, or you can install your own runner on a working machine, on a much more powerful machine, and we'll come to that also. And what else is to be said? There's a containerization or a Docker image. What means that this workflow can run on any machine, so I can run it basically on the free runners on gitlab.com. I can run the workflow on my laptop, on my working station, and a colleague could do the same on his working station, independent of the actual setup, or somebody would not even have to have OpenFOAM installed in the machine. So this is a great help for reproducibility as well. And then what would this YAML file look like this? We have a job name, would be the first line in the left part of the screen, an initialization step. It depends on build job, and then it just has some simple script where you can cd into some folder and execute some shell scripts, for example, and then produce artifacts. What would be, for example, the CSV and PDF files, and those are passed can be passed to the next job, and also can be downloaded by us later on. This would look done like this. Underline the stages, and the jobs are actually those items with the green arrow, or the we will look into this concrete CI pipeline later, so I don't want to spend too much time on this slide. As I already mentioned, we create job artifacts that are can be downloaded from GitLab. And right. Seems to be handy. When we run some studies on parameters or mesh conversions, for example. We would we have one folder, and inside this there are subfolders for each case that runs with the associated data, and write one notebook using some loops to go over all the cases inside and display convergence rates or parameter dependency of some results. And in the notebook, of course, there's the documentation sort of, or links to what we actually test, what we expect, how it should look like. The nice thing is you can connect those results to the internet. So if you have to run your studies on a high-performance computer, you can inspect them live, and if you see that the results do not match your expectations, you can abort the computing run and therefore save a lot of time. So basically, what I already said, plus you might think about HDF5 or XDR, what are two file structures for describing the parameter studies. And then you use Jupyter notebooks and pandas as well. What we are doing is documenting, processing, and analyzing with just these simple tools that are open in the sense of understandable to basically most people, or community. One more thing, you can convert the notebooks to the PDF and HTML files, anything that helps you include those files in the archiving, and and we have a look at the pandas files in a moment. Now, why do we do that? We might have some results that look like this on the right side. Want to point out the log scale outside. So it's basically impossible to judge those results, or even worse, if you would have a method and wanted to compare your results to that, it's impossible. So please provide the CSV file according that, or belonging to this. With in your publication and in your data archives. How might that look like? If you use multi-index CSVs, it's very simple, easy to automate all the evaluations, but you will repeat metadata. For example, here the shear 2D, it's always the same model, independent of the grid size, what is done in that table. But it basically doesn't matter, since this CSV file is expected to be a few kilobytes at most. So just included, that's makes life much more easy. So we basically covered all that is done in the yellow part by the automatically build and run pipeline. Now, 2-3 things more. We have to judge if the tests have passed. This might be possible sometimes by automated script. Sometimes a bit more hard, or might even have to have look into that, at least for new features. And for example, it might be a volume conservation, order of converges, and the total wall clock time that you could have in your test. Yeah, and then you put out these data, for example, in the CSV file, read them in with Python as a test, check if the order of convergence, for example, is near to this way to automate that. But there might be difficult things, so there are then a few options. You evaluate them by looking at the results. What, of course, becomes not very good if you have to do that very often. You could use some statistics like mean or root mean square error, or maybe compare that to some expected results, maybe even from previous runs. So you don't know if the solution is right, maybe, but you know it hasn't changed. Assuming that you were satisfied with the results from the previous run, seems okay. We already went a bit, or I already mentioned Docker to you. Yeah, already mentioned that. So the Docker container can be shipped and run on almost every machine, be it laptop, computer, or working station, or HPC cluster. This your needs depends, of course, your testing. Try to be fair. It's if you can, you should try to not have too much expensive tests. Once you try to go on an HPC cluster, it's usually much more difficult to set all the things up to work and to be like security and legally and so on and so forth. Okay, but yeah, try to concentrate on tests that you see, or maybe have a working station at the or something, core CPU. And this was that part. This is just for completeness, and I'd like now to take another look at a repository. Before that, let me point out at the bottom part, see a DOI where you have access to the slides. So all the links and so on and so forth included. Before we take a look to that code here, I want to make sure to point you to some more resources. As I said, if you note on the DOI, you get all the links. There's more material. There's Turing Way. There's NFDI for Ring. We do run knowledge base within the NFDI for Ring. We're much more hands-on and to code and code snippets are about this workflow and the tools that are used in there. There are much more initiatives like Better Scientific Software, for just for an example, and also, of course, we have more slides and preprints about that. So, okay. And coming back to the promised repository, we can have a look onto. This is a small OpenFOAM showcase. And as previous, we have a publication link there. This small repository. There's really an OpenFOAM case. And now, if we look into the latest pipeline, maybe, you see we added one more job, that is Docker build. So what basically happens is we, from time to time, build a Docker image with the OpenFOAM and push that to the package registry on GitLab. Container registry. My bad. Where we have then the container that is downloaded or that is used in the in those jobs. The code that has been developed is compiled, parameter studies are run, they are visualized, and then some Python scripts run over to assess if convergence, for example, has been met. And quickly, here we have the artifacts cases. Here now we get PDF MD from our CI pipeline. So we already, from the CI pipeline, have this PDF, this lovely diagram showing also nice convergence. Here there's a description of the thing that's missing, and another convergence that is worse looking. So we also can look into the X2D case. What is one of the test cases? We have CSV files that we could download. Same here, and we have pictures that were included in the PDF, which we could now take and put into any other report. And what does the actual pipeline look like? And this might be the slide is okay now. We start with the Docker image, and first thing that is done in the order of execution is this Docker build job, which only runs if we make changes to the Docker file. So this is not run every time, because simply it's not, there's no use in it. What we do is we build the Docker image and push it to our own registry. And that's basically all that happens from a functional standpoint here. And then in the next step, we compile the code. So the code that is inside this repository, and it takes the latest image that we uploaded or built here in the job before. Now I can look into the Docker file format. What is done here is we take recent, or well, almost recent Ubuntu. This is a long-term support version. In that case, we take the pre-compiled OpenFOAM version 2006 and install it. Install some additional packages we need for the visualization, like Jupyter notebooks and other Python stuff, as well as PyFOAM, what is used in the last test. Now, coming back to the pipeline after compiling the code in the repository, we run the parameter study, which is just some script that is executed, produces the CSV files, which are uploaded as the artifact and passed on to the next job, which takes those CSV files, runs a Jupyter notebook, and save that Markdown and PDF. We add that to the artifacts, and then we have two testing jobs. Basically using the Python for testing, and we'll look into that. 3 cases test convergence. So this is test convergence. It's 9 lines of code asserting that OLINF, what is the order of convergence of the infinity norm, is at least bigger than 1.7. And what we already saw, this is also what then fails in this pipeline. GitLab also to see that this was the line that actually failed, trace back, assert data, and there was the assertion error, and that's why we have one job that fails in this pipeline and one job that doesn't. All right, so with that, I think we're going to the questions. See a question in the chat. I'm also using field compares somewhere in these workflows. I know since I saw Dennis Glaser in the orders list. True. So Dennis Glaser is in the authors list of the paper, which is out as a preprint for some more months. By now, I'm assuming he did not have a field compare completed when this preprint was put out. It is, of course, would be one possibility for the tests. But also I think we do not or can try to circumvent that by using, for example, the convergence rate instead of field compare. But yes, that would be two. So, are there any more questions? I think has been a lot of topics on stuff.
Thanks for your talk. What would you recommend? So I'm working alone on some code, and I'm also using Docker containers and try to do a good job documenting everything. What would you say? Where should I start to do some kind of like the things you showed? But what would make the biggest impact if I changed anything in my workflow? Like maybe where should I start? Well, what would make the biggest impact to start now? What do you say?
But it's, of course, depends a lot on your actual setup and what you're already using or might not be. I guess in terms of the relation of work and game, one of the best and easiest thing would be to do this cross-linking. So, since, well, assuming you like write 1 or 2 papers per year, this is only a few hours maybe, and you have at least all your data findable. So if you think about the much used acronym FAIR, which is you might have heard of being findable, accessible, interoperable, and reusable. You at least have one of those 4 letters satisfied to a acceptable degree. And if you include your Docker files in it, you also have the reproducibility at least partially addressed.
Yes, we also have the database at our institute that so far nobody uses. It's supposed to have all the fair data. Do you see any possibility to integrate this into some kind of database? It's called Nomad. I don't know if you.
I might have heard that name before. We are at the TU Darmstadt, so we have a repository that's called TU Datalib, where we have the first example I showed you. So if it's just an data archive, I think, like Zenodo or back to the TU Datalib. Model. And well, that's very well integrated. I know there are people in Germany from the Helmholtz group which set up an automatic tool to push versions from the GitLab server to the repository. This is for our group not that useful because we only do this workflow or do this part of the workflow once every few months. But the Helmholtz people seem to do it daily or at least weekly.
Yeah, thank you.
There's not any question, and so thank you for your talk, and I think that we can close the session. There's another question.
Hi, Moritz. Thank you very much again. So you are comparing how the results may change and so on. Do you think that you can also get consistent enough performance regression comparisons with the GitLab runners and so on? Have you tried something like this?
Well, we didn't try performance studies on shared runners. I'm not aware that this is something that people do. I would be a bit astonished if that really is the way to go, because you have the free runners. I might confuse that now with the free runners from GitLab or GitHub. I think you have 1 or 2 cores. You have very limited memory. I would assume that you don't always have the same hardware, but sometimes some older or some newer CPU generations. So that's my point on that.
Thanks.
You're welcome. I just close. All right. So then, thank you for attending and your questions. Yeah.
Thank you for your presentation.
You're welcome.
Perfect in
What
time.
Yeah. Likewise. And welcome. Hopefully hear from you again.